It cuts right to the heart of one of the most fascinating mysteries in modern astrophysics. Dark matter is, by definition, invisible. It doesn't emit, absorb, or reflect light. Yet we're pretty confident it makes up about 85% of the matter in the universe. So how do we see something that's invisible? The answer lies in its gravitational influence. Dark matter may not interact with light, but it absolutely interacts with gravity. That's what gives it away. One of the most powerful tools astronomers use is gravitational lensing. Think of space as a stretchy fabric. When you put something massive, like a galaxy cluster, on that fabric, it bends. Light traveling through this warped space gets distorted. It's like how a magnifying glass bends light to make things look bigger or warped. When we observe distant galaxies behind a massive object, the way their light is bent tells us about the mass in the foreground, even if some of that mass is dark matter. There are two main flavors of gravitational lensing: strong lensing and weak lensing. Strong lensing is dramatic. Light gets so bent that we see arcs, rings, or multiple images of a single galaxy. Weak lensing is more subtle. The shapes of background galaxies are slightly stretched in a statistical way. If you look at enough of them, you can measure this average distortion. You can build a map of the unseen mass that caused it. Large surveys like the Dark Energy Survey, or Euclid, scan the sky for these tiny signals. They turn them into a cosmic map of dark matter. Another method is the study of galaxy rotation curves. In the 1970s, astronomers like Vera Rubin discovered something strange. Galaxies weren't rotating the way they should if all the mass was in stars and gas. Instead of stars slowing down farther from the center, they kept orbiting at roughly the same speed. The only explanation was a massive, invisible halo of dark matter holding everything together. On larger scales, we look at the cosmic microwave background, or CMB. The CMB is the afterglow of the Big Bang. Tiny fluctuations in the temperature and density of the early universe were mapped by satellites like Planck. These fluctuations carry the fingerprints of dark matter. These measurements, plugged into simulations, show how dark matter must be distributed today. That's how the galaxies and clusters we see now could have formed. But no method is perfect. There are real uncertainties. With gravitational lensing, you're not measuring dark matter directly. You're measuring its effect on light. This depends on knowing how far away the background galaxies are, and their original shapes. Any small bias in your assumptions can ripple through your entire dark matter map. In galaxy rotation curves, you're assuming the mass-to-light ratio of stars, the gas contribution, and the galaxy's geometry. All of these can introduce errors. Another challenge is that all our evidence is gravitational. What if something else can mimic these gravitational effects? Modified gravity theories like MOND try to explain galactic motions without dark matter. But they struggle to explain lensing and large-scale structure at the same time. We still don't know what dark matter is. It could be WIMPs, axions, sterile neutrinos, or something even weirder. This adds an unavoidable layer of uncertainty. Mapping dark matter is like reconstructing the shape of an object underwater by looking at the ripples. You can't touch it or see it directly. But with enough ripples and a good model, you can figure out what lies beneath. We've gotten remarkably good at it. But we're still searching for that one discovery, the detection of a dark matter particle in a lab. That will finally let us connect the map to the substance itself.